Charles Martin here with Calculated Content. Thanks again for joining us. Today, I would like to speak about a model from statistical mechanics that can help you to understand more why Weight Watcher works. It really is foundational to the theory behind it. So today's talk is entitled Spin Glass Models of Neural Networks, the Curie Weiss model from statistical mechanics. Now, you may be wondering why we care about statistical mechanics so much, and it's because it provides the theoretical framework for what we can do with the Weight Watcher project. And typically, historically, statistical mechanics has really looked at spin systems. And you may be familiar with certain kinds of spin models, like, say, the Hopfield model for neural networks. But there actually is a much simpler spin system that can describe basic memory and learning in a neural network, and this is called the Curie Weiss model. So let me sort of start off by just explaining some of the math. We're going to go through the math in some detail so you can understand some of the techniques that are used later on in more sophisticated treatments, such as our semi-empirical theory of learning. You start off in statistical mechanics by specifying a Hamiltonian. So the Hamiltonian describes the energy of the system. Here, you write the general form H as minus sum I less than J, or all pairs Ij, it's what that means, of Jij, which is an interaction term, times sigma I, sigma j. And the sigma I, sigma j are spin variables. They're either plus or minus 1. So you're summing up over all possible plus or minus 1 spins in the system. And then you subtract off this term sum over I, hi, sigma I, where h is an external field. So the model for this is something like the J represents the weights in the layer of a neural network. The sigma I and sigma j represent the sigmoid inputs and outputs. And the H term is like training a supervised learning algorithm. You're putting some sort of field, or you're tying the outputs to some sort of label. So we can get an idea of why you would use a spin system to describe this. You may recall that typically an activation function you might see in a neural network is a sigmoid. And this figure represents a picture of a sigmoid where sigma I is plus 1 is denoted by this arrow pointing up. And that corresponds to the area of the sigmoid where x is way out here, like past 2. So this is when x is very large. When x is very small, the sigmoid takes a minus value and you get a minus 1. So you can represent the outputs of a neural network as just simply plus or minus 1 spins. This is a very, very old idea. It's the sigmoid itself was introduced by Jack Cowan, who was a friend of my advisor at the University of Chicago, and it was introduced to represent the inputs and outputs of a spiking neural network. And it was really guys like Hopfield who recognized that you could map the spins of a neural network to a spin glass. Here, the simplest spin system ever is much simpler than the Hopfield network. It just says that you have a Hamiltonian where J is constant, and you divide by 2 over m, which is the number of normalization. And here we're summing up over all Ij. And we have and since we've doubled the sum, we have a half here because we're summing up over all Ij. So we have minus J over 2n times the sum over all possible inputs and outputs. And the reason you would do this is because it's a very simple but powerful model which captures the fundamental behavior of phase transitions in a system. And by phase transitions, I mean the transition between learning and forgetting. If you look at other theories, in particular statistical learning theory, machine learning theories, they don't treat phase transitions at all. Or maybe they try to now because they recognize there are things like double descent or grokking, which are really phase behavior. And using a tool like Weight Watcher, you can describe double descent and grokking very easily. And it's because we use statistical mechanics. So statistical learning theory, other theories don't really describe phase transitions well. But here it's very simple. And even the simplest model, the simplest Curie Weiss model, demonstrates this basic behavior. We're going to look at something called a mean field approximation. And we're going to describe mathematically what that is. And the mean field approximation is going to treat each spin as if it's interacting with an average field. This is a mathematical trick we use in statistical mechanics. It's also used in quantum chemistry. It's a little different the way we do it, but it's a trick that's used to simplify the interactions in the problem. And what's going to happen is once we do this, we're going to define an order parameter. The order parameter will be the magnetization. The magnetization will be like the memory. Think of M as magnetization or memory. And it will tell how much the system is memorized. And this will distinguish between the two phases, between memory, basically memorizing and forgetting, or learning and not learning. And this will later be connected back to a hot field model in associative memory, which we'll talk about later in another video. But the main thing we want to do is derive this result, where the average magnetization is the hyperbolic tangent of beta Jm, where beta is the inverse temperature, J and J again is this coupling constant. So this is a nonlinear equation. The average M depends on average M, so you have to solve this equation nonlinearly. And we're going to show how we can derive this equation very easily using a little statistical mechanics and a mean field approximation. The physical picture here, why would you use this? Why do we call them spins? You could think of the sigma I as being a little magnet or a little spin that points up. So you give the arrow as the top being the North Pole and the bottom here being the South Pole. And you think of a bunch of little magnets that are oriented. So you might put a bunch of little magnets on the table. Really, this model comes from taking a metal and putting magnetic impurities in it, little pieces of iron inside a metal, and each little piece of iron is magnetic, and and they're all weakly interacting with each other. And when the temperature is very high, so the temperature is above the phase transition Tc, this critical temperature, when the temperature of the system is very high, all the spins or the magnets sort of mix around themselves however they want, and you have random spin orientations. And this is a model of a system where the average magnetization is 0, so average M is 0, or it has no memory, memory is 0. There's high thermal noise, which destroys the correlations. This is analogous to an untrained neural network. So this is analogous to when you start training your neural network, you give it a random matrix to initialize the weights. This is the model. There's then another phase we'll find, which is the ferromagnetic phase, when the temperature is low. When the temperature is low, all the spins add up. So it's like the system has memorized some pattern. The spins have all aligned. So this is the ferromagnetic phase. The spins align, meaning the magnetization, or in this case, the memory is greater than non-zero, will be greater than 0 in this case, as they're all pointing up. The system has some sort of structured order. And this is analogous to a neural network, which, I'm sorry you can't see it, where all the memories are stored. So the memories have been stored. So what we're going to see is that learning is a phase transition. The act of learning in a neural network corresponds to moving from disorder to order. So before training, you're in a paramagnetic state where you have random weights. During training, the system will approach near criticality. The learning increases the correlations in the system. And after training, you end up in a magnetic state where the patterns are stored and retrieved forever. And again, you get this nonlinear equation for the magnetization. Now, if we plot that equation for the magnetization versus temperature, where Tc is J over Kb at this point, this is where the transition occurs. And again, when you go back to the equation, beta is 1 over kBt. This is an inverse temperature. If we plot average M as a function of temperature, you see that the average M as the temperature goes at T equals C, at the critical point, M is 0 at this critical point. And when T is above 0, T is above 1, then there's no magnetization. So whenever the temperature is above this critical point, you get a sharp transition. When the temperature is below 1, then you see that you can actually get some order. And you see the order is somewhat continuous until you get to a very, very low temperature. Now, moreover, there is right near the critical point, if you zoom in this little region, you'll see that there's power law behavior near the critical point. This is actually an important feature as well. When you get near in the inset, you see this power law decay near the critical temperature. And this is something that Weight Watcher actually takes an advantage of. But today we're just going to look at just generally how to derive the shape of this curve. And in fact, you can do measurements on metals, like in actual systems, and you'll get a curve. You'll get curves which are similar to this. Obviously, a real system has a lot of structure, but this is a very simple model for a real system, and it turns out it captures really the physics of what happens in learning. So let's go through the math and see how this works out. We start off with Hamiltonian, again, minus 1 over 2n, where j is minus j over 2n. 2n because we're counting we're counting the pairs, and we're kind of double counting, so we have to have 1 over 2. All spins, and the j is constant. So we begin with this Hamiltonian minus j over 2n, sum ij of all sigma I, sigma j. We're going to define the magnetization. So the magnetization is just 1 over n times the sum of I equals 1 to n sigma I. So again, the magnetization, for example, in this example I showed you earlier, we looked at, here the magnetization would be 1 because you have all the spins are pointing up. If the spins are pointing the other direction, the magnetization would be minus 1. And if the spins are random, the magnetization is 0. So the average magnetization. So this is really the magnetization. We'll note that if we sum up over all the spins, we would get n squared times m squared. So the sum of all the pairs is n squared over m squared. That would be the total sum. Thus, we can write the Hamiltonian as minus j over 2n n squared over m squared, or minus jn over 2 m squared. So notice that the energy scales as n. It scales as the number of spins. This is a property in physical mechanics or thermodynamics, meaning it's extensive. If you increase the size of the system, the total energy in the system increases linearly. This is important because now that we have a system that scales as n, we're going to take a mean field approximation. In the mean field approximation, this MF means mean field, means we're going to describe the system as a single spin embedded in the lattice or in the material. So we're going to call the mean field Hamiltonian minus j over 2 m sigma I, where if we sum up over all spins, again, we insert this HIMF into the sum over all I, and we sum up over all, and we again would get jn minus jn over 2 m squared. So again, we just took this Hamiltonian, we stuck it into this, we stuck that mean field Hamiltonian into this, so we replaced the sigma I with this mean field Hamiltonian, and we sum up. So now notice we can write the total Hamiltonian in terms of a sum over Hamiltonians of a single particle. So instead of taking a sum over ij, we now have a sum over a single spin I. And when you do this, you're going to get a self-consistency equation that says m equals tan h beta jm. And our goal is to derive this equation. How do we do that? Now, more rigorously, what we're going to do is we're going to show that a mean field approximation arises from taking a saddle point approximation and at large n. So what does this mean? What is a saddle point approximation? Well, we're going to start by writing down the magnetization, again, 1 over n times the sum of all the spins. And now we're going to write the partition function. The partition function is the integral over all spins, e to the minus beta n times n beta n and times some energy function f. So this is a partition function. We didn't really talk about that, but you can define the partition function as given a Hamiltonian, you would write the partition function as the sum over all spins, e to the minus beta h. And you would then have a free energy. The free energy is defined as minus 1 over beta log z, where beta is 1 over the inverse temperature. And your goal in training a model is to minimize the free energy. So we're going to take this partition function, which is a standard object in statistical mechanics, and we're going to write in terms of an integral over all m times e to the minus beta n f of m, where f of m is some function we want to determine. So we're trying to figure out what the partition function is at large n. So again, if we go back and look at the partition function, it's back here. Normally you would sum over all spins. Instead of summing over all spins, what we're going to do is we're going to integrate over all possible magnetizations. So we integrate over all possible magnetizations of the system, and we have to have some function f which depends on the total magnetization. Why can we do this? Well, again, we took this 1 over n sigma I and we plugged it into this equation above to get this expression for the mean field Hamiltonian. So we can write the partition function in terms of the total sum over all the spins. So basically, we factored out one of the sums. Now, what the idea is that you then can evaluate this integral using a saddle point. So the saddle point means if we have an integral of the form e to the minus beta nf, where n is large, we can approximate this by by removing the integral altogether and just saying z is approximately e to the minus beta in f of m star, where m star is the value that f of takes at its saddle point. That is f of m star. M star is where df dm is equal to 0 at that point. So this is called the saddle point. And this is so we approximate this integral by taking this by its peak value. So why do we do this? So in higher dimensional functions, a saddle point is a stationary point where the derivatives vanish. It is neither a pure minimum nor a pure maximum. In statistical mechanics, when taking integrals over large N systems, the saddle point, or methods of steepest descent, approximates integrals by expanding them around the function's stationary point. This is a very common technique. If you read our paper on Weight Watch or the CETO paper, we discuss the saddle point in more detail, but the idea is that the approach leads to a mean field solution of the Curie Weiss model in the limit as n goes to infinity, which is really in the limit as n being very large. It doesn't even have to go to infinity. So again, we have the spins sigma ij, which are minus plus 1. We have the Hamiltonian minus j over 2n, sum over sigma ij minus h over sum over I sigma I. J is greater than 0, means we get ferromagnetic coupling, and h is the external field. This simplifies to minus j over 2n sum over sigma I squared. Sum over sigma squared. This is the total minus h sum over sigma I. And this now begins to look like the total magnetization squared. So again, we see 1 over n times this sum is the magnetization. So we can rewrite the Hamiltonian as minus j in over 2m squared minus h in m. I would encourage you to, if you don't see this for yourself, I would encourage you to sit down with a piece of paper and write this down, stick m into h, and show that you can rewrite the Hamiltonian in this form. So we expect m to be the relevant order parameter that indicates the phases. So once we have the Hamiltonian in terms of m, we're now going to write the partition function. The partition function is e to the minus beta h, where beta again is 1 over kbt. We substitute h into this expression, and we get z as sum over all sigma I, exponential beta j n over 2 m squared plus beta h in m. Again, I encourage you to try to derive this equation and then take h, stick this h into z, and write it down. You'll get this expression. But now we notice that since m depends on the sigma, we have to enforce this constraint. This is a key idea. Because we want to change variables, we're going to change variables from integrating over sigma to way back here to integrate over m. And to integrate over m, we have to change. We're going to do a change of variables. So to do this change of variables, we're going to introduce a delta function. Again, this is a very common technique. And when you read the semi-empirical theory paper for Weight Watcher, you'll see that we do this several times. So that's why we're going over this. So I want to enforce the constraint that m is 1 over n sum over sigma I. So I'm going to write an identity operator. I'm going to say 1 equals integral over dm delta m minus 1 over n sum over I to n sigma I. So I now have expressed this constraint as a delta function. I can then take this and represent the delta function using a Fourier representation. Delta x is 1 over 2 pi integral of minus infinity to infinity e to the I lambda x d lambda. And I can substitute this. Now I can now stick in this m minus 1 over n, the sum, for x. And I'm going to do that. And when you do that, you're going to get this new integral. So instead of now, we're going to integral over dm, which is over the magnetization, and integral over lambda, which we're going to call a Lagrange multiplier, because it is a parameter which it parameterizes our constraint. And then we have our original sum over, now we substituted in this term for the delta function, and now we have again the second term, the beta, these terms in beta, which came from the Hamiltonian, which is expressed in terms of m. So now the total z is now expressed in terms of an integral over m and an integral over a delta function. Now we're going to factorize things. So now we have to be a little clever. And we're gonna factorize the spin, and we're gonna simplify it, because we're gonna turn this complicated expression for z, this partition function, into this simpler expression for Z. It looks simpler because it turns out that this sum, if you take the sum over an exponential I over all possible spins, this actually ends up to be 2 cosine lambda over n. If you haven't seen this before, you want to think about it for a while, but it's basically, the n factor, this n is coming out here because a sum of exponentials is a product of the product of terms, and each term is, you have cosine, which is if you know anything about complex analysis, you'll recognize that cosine lambda over n is e to the I lambda over it. You can express cosine lambda over n in its complex form. And if you go back and take a look at what the complex form of cosine is in terms of exponentials, this expression should be very straightforward for you to derive. So we obtain this expression 2 cosine lambda over n. We're going to just replace this conjugate variable, or this Lagrange multiplier, with phi, so for simplification, and we take a change of variables, d lambda is n d phi. And now we rewrite the partition function as z is integral of dm, again the magnetization or the memory, n over 2 pi, minus infinity to infinity d phi, times the exponential of this term I phi m, plus beta j over 2 m squared, plus beta hm, plus natural log 2 cosine phi. At this point, you may not think we've actually simplified things, but we can actually write this term in the exponential in terms of S m phi. In physics, this is sometimes called a mean field action. S is just an action. So when we simplify, we're going to get this term in terms of S. Now we can apply the large n approximation. So what we do is we have this complicated integral in terms of e to the n, in terms of exponential ns. We're going to take the large n limit. N goes to infinity, or just n large. It doesn't have to be really infinity. We don't really reach the saddle point here. In the paper, we try not to use this notation because it's a little confusing, but the integral is dominated by taking the extreme values. That is, you satisfy the stationary conditions. So you take S and you say, I want to find the first derivative is equal to 0 in terms of m and in terms of lambda, because I have, well, that's okay. If you take, it's not obvious that you take S, we've actually expressed it in terms of phi, but here I did in terms of lambda. But if we take the derivative, you'll see that m is tan h lambda. And if you see ds dm of 0, you're going to get lambda plus beta jm plus beta h equals 0. If you eliminate the lambda, you find m is tan h beta jm plus beta h. This is the self-consistency equation we are attempting to find. So again, what have we done here? And I'm sorry, this might not be as clear because I wrote phi here and lambda here. I'm sorry about that, but if you work it out, I'm sure you'll find it works out. So if you go through and do the expressions yourself, you will find that all we've done is taken this S, we've applied the saddle point approximation by finding the stationary conditions, and by taking the derivative of this, we find that we obtain this self-consistency equation. Now, given the self-consistency equation, we can analyze it. For h equals 0, when we have no, now we'll take the case where h is 0, so there's no field, and now it simplifies. We take h equals 0, and again, I guess we could have done that the whole time. We didn't really have to carry this h in here if we didn't want to, but that's okay. At h equals 0, we find m is tan h beta jm, so the average magnetization is tan h beta jm. This is the result we're looking for. Recall beta is 1 over t, so we can actually solve for this, and we can find the plot that we had earlier, which is, recall we had this plot of the equation. You could try plotting it yourself. See if I can find it for you. No. Here. So we're actually plotting. We've now derived this equation for m. And you see that when the critical point occurs, when TC is J over K, we can just set K equal to 1 for our purposes, since this is not a really physical system. If beta is less than beta C, T is greater than TC. The only trivial solution is M equals 0 is paramagnetic. And if beta is greater than BC or T is less than TC, then the non-trivial solution is M not equal to 0 is ferromagnetic. And so we get a spontaneous magnetization, or spontaneous magnetization occurs below T is TC. We can also define something called the magnetic susceptibility. So when H is not 0, we say, well, let's take psi as dmdh. So in other words, how does the magnetization change with the applied magnetic field? And if you work out this derivative, you'll obtain an expression that this psi is dmdh. This was beta over 1 minus beta j. This diverges at beta j equals 1. So this is important to understand. What does a phase transition mean? A phase transition means that something like the magnetic susceptibility or other terms will diverge. So you get a divergence at this term. So as you turn on the field, as the field goes to 0, you get a divergence. This signals the phase transition. So in conclusion, what have we done here? We've taken a look at the Curie Weiss model, which is a model for the interactions between terms in the layers in a neural network or spins in the spin system. And we've shown that you can write down a simple field field description. We then used the saddle point method, and we derived the self-consistency equation, m equals tan h beta jm plus beta h. And again, I encourage you to sit down and work through this yourself by hand. I will post these notes online so you can see them. We show that below the critical temperature, the system requires spontaneous magnetization at m not equal to 0, and above the critical temperature, it is disordered. So this is a basic idea. I wanted to walk through it with you so you can see how you can apply the saddle point approximation and the mean field approximation, saddle point, large N, for a very simple problem, and you can work out actually seeing the phase transition that occurs. These are mathematical techniques that, again, we use in the semi-empirical, the paper for Weight Watcher, the theory paper for Weight Watcher, semi-empirical theory of learning. We use these techniques extensively, so I wanted you to see them in a simple context or an area where you can work them out by yourself, by hand, to get a much better understanding of how the theory works. And as I said, this methodology underpins many mean field theories, including hot field networks in computational neuroscience, large areas of theoretical physics, statistical mechanics. This is sort of like if you can grok this basic stuff here, you'll be well on your way to understanding a lot of these statistical mechanics models. I hope this was helpful to you. And if so, please leave feedback. Join us on the Weight Watcher Discord channel, and we'll be discussing a lot more of these things in the future. Thanks again for joining me. Once again, Charles Martin, Calculated Content.